Hello everyone. Today we are going to discuss some more topic regarding say neural networks. Myself Dr. Amit Kumar Yadav, Assistant Professor, School of Computer Science and Artificial Intelligence, SR University, Warangal, Telangana, India. First we will take say back propagation neural networks. In these neural networks learn from data by iteratively adjusting their weights to minimize the error between say output value and say predicted value. It is foundation of modern deep learning, and it enables training of complex neural network architecture on large scale data set. It include natural language processing, reinforcement learning, and image classification. It is based on mathematical concept, particularly linear algebra and calculus. First concept here is a chain rule of calculus. It relies heavily on chain rule of calculus, which state how to compute derivative of a composite function. In context of neural network, chain rule is used to compute the gradient of loss function with respect to bias and weight of each layers. Here loss function means error function, which is different between say which is difference between say target variable and say output variable, which is given by the network. The optimization technique which play a very important role here is say gradient descent algorithm, which is used to update the weight and bias of neural network during backpropagation. The important idea behind this gradient descent algorithm is to adjust the weight and bias in direction of negative gradient of loss function to minimize the losses. So basically gradient descent algorithm, it works on minimization of the loss function, that is the error function. So we have to compute here negative gradient of the loss function. Based on this negative gradient of the loss function, weight and bias are adjusted. Matrix calculus, it processes data in batches, making matrix calculus crucial for efficient computation. The computation involves in say forward pass and backward pass, which can be expressed using matrix operation such as matrix multiplication, element wise operation, and matrix derivative. Activation function, for example ReLU, sigmoid, tan hyperbolic, it introduce non-linearities in the networks. By doing so, networks are able to learn complex relationship in the say data. When we take derivative of this function, they are used to compute the gradient during backward pass. Loss function is a quantified the discrepancy between say predicted output of the neural network and actual target value. Derivative of loss function with respect to network output is the key component in computing, say, gradient during backpropagation. Next, here we are having, say, vectorized operation. To improve backpropagation and computational efficiency, vectorized operation is implemented. It allows parallel computation of multiple activation function and inputs, which speed up the training process. Then we are having regularization techniques such as, say, L2 and L1 is used to prevent, say, overfitting during training. These techniques introduce additional terms into loss which affect the gradient computed during backpropagation. Learning rate, it determines step size which was taken during gradient descent. So selection of an appropriate learning rate is important for, say, conversion and, say, stability during the training. Now, derivative of learning rules in context with backpropagation, it involves derivation of gradient with respect to weight and bias of the network. And these gradients are used to update parameters of the network using an optimization algorithm like gradient descent. Simplified error matrix which are used for single layer feed forward neural network is mean square error as the loss function and gradient descent as optimization algorithm. So considered here with one network, one hidden layers which consist of an input layers, hidden layer and output layer. Let's denote here X means input vector, W1 here weight matrix connecting the input layer to hidden layers, B1 as a bias vector of the hidden layer, W2 is a weight matrix which connect hidden layer to output layer, B2 is a bias vector of say output layer, Y is the output of networks, Y cap as a target output, sigma here say activation function, example sigmoid or ReLU. L is say mean square error loss function. Forward pass of the networks computed the predicted output Y. So in first case Z1 here weight matrix is multiplied by say input plus here bias B1 and it will pass through the activation function through um, activation function which are used in say neurons. Therefore here H is equal to say sigma times of Z1 and after this output of say hidden layer it will go through say output layers. Therefore here Z2 is equal to W2 connecting bit matrix between say hidden layer and output layer and it is multiplied by H plus here bias matrix at say output layers. And in output layers we are having say uh, neurons activation function Therefore, it will pass here y is equal to sigma times of Z2. Now, loss function L means the difference between say predicted output y and say target output y cap, and it is given by say L is equal to half y cap minus y whole square. Now let's compute gradient of loss function with respect to weight and bias using chain rule of differentiation and backpropagation. We have to compute here the gradient. And this loss function is dependent on when we observe here say connecting weight matrix bias, again here connecting weight matrix between input and hidden layers, and say bias of say hidden layers. Therefore, in backpropagation algorithm, we have to apply say chain rule of differentiation. Now here we will go from say output layers. So in output layers we are having say loss and we are having bit say W2, and output layer we are having say loss and bit here say B2. Therefore, partial derivative of loss with respect to W2, how we can write this one? Partial derivative of loss with respect to y into partial derivative of y with respect to z2, and here partial derivative of z2 with respect to y2. And we know that partial derivative of L with respect to y, it will give you here y minus y cap. And y with respect to z2, here we get here sigma dash z2. And when we will take say partial derivative of say z2 with respect to y2, here we will get h, and partial derivative of z2 with respect to b2, here we will get 1. Now again we have to go we have to take partial derivative of loss with respect to bias 2, which is bias in the say output layers. So here chain rule of differentiation, partial derivative of loss with respect to y, again here partial derivative of y with respect to z2 into partial derivative of z2 with respect to b2. So we will put all this value here. Then we are having say hidden layer gradient. At hidden layer gradient, partial derivative of loss with respect to W1 and partial derivative of loss with respect to P1. So here partial derivative of loss with respect to say H into partial derivative of H with respect to Z1, partial derivative of Z1 with respect to say W1. So here partial derivative of loss with respect to EH. Here we will take partial derivative of loss with respect to y into partial derivative of y with respect to z2 into partial derivative of z2 with respect to del h. Now here partial derivative of h with respect to z1, here we will get sigma dash z1, and partial derivative of z1 with respect to w1, this part we will get here x, and partial derivative of z1 with respect to b1 with respect to b1, here we will get 1. So we will put all this value here. This is called as a hidden layer gradient. Next, the learning rate alpha, which determine step size taken in direction opposite to the gradient. This alpha act as hyperparameters, and it should be carefully selected so that convergence and stability during training take place. If we take large value of alpha, it causes optimization process to oscillate or diverge. And if we take say a small value of alpha, it will slow down say convergence process. Overall bias and weight updated during gradient descent, which are essential for training neural network, and it enables to learn from data by adjusting their parameters to minimize the loss function. So number of hidden layers in neural network architectures should be selected carefully, and it is just a complex task which is based on say available data, computational resources, validation and experimentation. It is done through evaluation metrics for determining the optimal architecture of the specific task. Now, numbers of hidden layers. It is an important features of say neural network architectures that has big impact on both performance and computational complexity. The quantity of data that is available, the processing capacity and difficulty of tasks all play an important role in determining how many hidden layers to use. Neural network can contain any number of hidden layers in practice. For example, perceptron can have none, while deep neural networks can have several hundred. Typically, as a network has more hidden layer, it may learn more complicated patterns and representation, which could lead to an improvement in performance. Best architecture for specific tasks is frequently determined through trial and tuning. There is no hard and fast rule about number of hidden layers. Then here associative neural networks. It is association is a salient features or important features of human memory. Associative memory models. It is also known as content addressable memories, are a class of most extensively analyzed neural network. A pattern can be stored in memory through say learning process. For imperfect input patterns, associative memory have the capability to recall the stored pattern correctly by performing a collective relaxation search. Associative memories, it can be auto-associative or heteroassociative. For heteroassociative, output and input vector range over different vector space, while for auto-association, both the output and input vectors range over the same vector space. Heteroassociative neural networks, it is known as heteroassociative memory (HAM). It is a types of networks which is capable of associating patterns of different types. Unlike auto-associative memories, which map pattern to themselves, heteroassociative memory map one type of pattern to another. During training, the network is presented with pair of input-output patterns and adjust its connection bits accordingly to learn the association between them. Once network is trained, the network can recall an output pattern given its corresponding input pattern or vice versa. Heteroassociative memory have application in various fields which include say pattern recognition, information processing, and associative retrieval. It is used in say image recognition tasks where input image is associated with a corresponding label or category. Then here we are having auto associative nets. It is called as AANN. It is simply known as auto associative network or auto encoders. It aimed to learn to reproduce its inputs at its output layers. It tried to reconstruct its input data from a compressed or say encoded representation learning during training. So basic architecture consists of an say input layer, hidden layer and an output layer. In hidden layer we are having say multiple hidden layers. So number of neurons in hidden layer is usually smaller than number of neurons in input layer and output layer, which forces the network to learn a complex representation of the input data. Auto-associative networks, it is trained using unsupervised learning architecture such as backpropagation or variant like Hebbian learnings. During training, the networks is presented with input data and weights are adjusted to minimize the reconstructed error. That is, the difference between input and output. Once training is complete, the network can be used to reconstruct simple pattern to those it was trained on. Auto-associative application, it is used in say data compression such as say signal compression or say image compression. In features learning, so autoencoders can learn useful features or representation from say raw data. Then it can be used as input to other machine learning models for say classification or say clustering tasks. Noise reduction. Autoencoders learn to reconstruct input patterns. Therefore, it can be used to denoise or remove noise from the data. Anomaly detection. It can be trained on say normal data and then used to reconstruct unseen data. The significant difference between original and reconstructed data can indicate anomalies or outliers. Here we are having say bidirectional associative memory. Bart Cosco invented the concept of bidirectional associative memory in 1988. It is just a kind of neural network architecture. This associative memory is able to remember one pattern when presented with another. It is called as a BAM. It is a heteroassociative memory as opposed to auto-associative memory, which recall patterns that are comparable to those stored in memory. Recall pattern from one set, given pattern from another set. Two layers in, say, bidirectional associative memory, inputs and output layers. Input layers neurons is fully coupled to every output layer neurons and say vice versa. During training process, the bits which are connected among the layers teach the network to identify patterns in the networks and output set. When training a bidirectional associative networks, pair of outputs and input patterns are given to it, and Hebbian learning or other reinforcement learning principles are used to modify the connection bit. After being trained, the network may remember an input patterns that correspond to an output pattern and vice versa. Bidirectional associative memory application. First one here say pattern recognition, where input patterns need to be associated with corresponding output patterns. Its applications are in say various domains such as speech recognition, image recognition, and character recognition. Then here we are having associative retrieval. Bidirectional associative memory. It is used to retrieve associated information based on input cues. For example, in information retrieval system, BAM can help in retrieving relevant document or data based on query. Mapping between different types of pattern. Bidirectional associative memory is useful when there is a need to establish association between patterns of different types. BM can be used to associate word embedding with their corresponding meanings or concepts. Data compression and reconstruction. So BAM network are used in say data compression tasks where it learns to compress input patterns into say lower dimensional space. You can say that from higher dimensional to lower dimensional space and then reconstruct back to say original form. Therefore, it reduces storage requirement for say larger data sets. Anomaly detection, uh, where this network learn to associate normal pattern with their expected output. So when there is any deviation from expected output, it indicate anomaly or outliers in say input data. Now here back propagation, one can practice say simple numericals here. Here we are having say input which is given as a 0.05, input to 0.10, and here bias value 1. Here we are having connecting bit say W1 minus 0.15, W2 0.20, W3 0.25, W4 0.30, and hidden layer neuron H1, H2, and again, and this is the connecting bits H1 to output layers, and here say minus 0.40 bit values, Here value W5, W6, W7, W8. Here we are having 0.01, here 0.99. So here we want to output say activation function is logistic. So whole solution of this one can be found on this link. Now similarly we are having another networks for this is against a back propagation networks input layers, and here expected output means here target value is given. So we have to go for say forward pass, and then we have to calculate here say error. So based on this error we have to go for say chain rule of differentiation and calculate the updated bit. Whole solution can be found on this link. One here say adaptive resonance theory. It is also called as say ART. It is proposed by Stephen Grossberg in field of artificial neural networks. It is a neural theory and cognitive, and it is designed to explain how brain might learn to categorize and recognize objects and events in a changing world. It is inspired by brain's ability to categorize and adaptively learn from new experience. It remains stable in the face of changes. It it includes two main components. First one, top-down processing. Second one, say bottom-down processing. Bottom-down processing incorporate recognition of incoming sensory patterns, but in top-down process it involves say feedback signals which modulate the recognition process based on prior knowledge and expectation. The different features of ART networks is their ability to dynamically adjust their category boundaries in response to new information, but it maintains stability through a process called as resonance. When new input is presented to these networks, the system compare it with existing category, what it is having. If input is similar to existing category, it resonates with that category, reinforcing it. If input is different from existing category, the network formed new category. This whole process allows this ART network for learning and adaptation to new information. But during this process, the network cannot forget previously learned pattern. This network has been applied to say various domain, which is called as say pattern recognition, cognitive modeling, and classification. The application of this network are say speech recognition, computer vision, and say machine learnings, where adaptive and robust learning systems are required to handle complex and dynamic environment. What are say main operation of ART classification? First is say here recognition phase. In recognition phase, input vector is compared with classification presented at every node in the output. The output of neurons become 1 if it best match. Otherwise, it become 0. Comparison phase. In this phase, the comparison of input vectors to the comparison layer vector is done. The reset condition is that, say, degree of similarity would be less than vigilance parameters. Search phase. The network will search for reset as well as match done in the above phase. Hence, if there would be no reset and match is quite good, then classification is over. Otherwise, the process would be repeated and the stored pattern may be sent to find the correct match. This is the say pictorial diagram of say ART networks. So here you are having say input layers. Next here you are having say interface portion. After this here we are having this clusters units. Application of say ART networks. Here we are having in say mobile control robot for controlling say different steps of the robot. Then we are having this signature verification. Then we are having say target recognition and medical diagnosis. So this is the pictorial diagram of say ART networks. So here it is designed for binary input vectors. This portion, here we are having input layer, then here layer we are having say interface portion, here we are having this cluster unit. This network consists of two fields of unit input called as a F1 unit and output unit which is called as a F2 unit along with reset control unit for controlling degree of similarity of patterns placed on the same cluster unit. So here we are having this reset control units. What is the function of this reset control unit? It controls similarity degree of patterns placed on same cluster units. Computational units of ART1 networks. It consists of say input units. It is called as F1 unit. So both input portion and interface portion. Then we are having this cluster units. It consists of F2 units called as a output unit, reset control unit. What it do? It controls say degree of similarity of patterns which is placed on say same clusters. ART2 networks. Uh, it is used for continuous valued input vectors. The complexity of ART2 networks is higher than ART1 networks because much processing needed in F1 layers. So in F1 layers, we require more processing units. Therefore, complexity arises in ART2 networks. This ART2 networks is designed to recognize category for binary as well as analog input sequence. So in ART2 networks, continuous valued input is presented to the ART2 networks. It may be of say two form. The first form is a noisy binary signals form, and second form of data is truly continuous. What is the major difference between say ART2 and ART1 networks? Is the input layers. Here a three-layer feedback system in the input layers of ART2 networks is required. A bottom layers where input patterns are read in top layers where input coming from output layer are read in, and a middle layers where the top and bottom layer patterns are combined together to form a meshed pattern, which is then feedback to the top and bottom input layers. Then we are having this learning vector quantization. It is a type of say supervised learning, machine learning, which is used for say classification. Its mainly goal is to create a set of reference vectors which represent the data in such a way that help to classify new data. In LBQ, data is separated into clusters, and a representative vectors or prototypes is assigned to each clusters, and these prototypes are adjusted during training phase for better representation of data. The adjustment process involves moving the prototype closer to say data points. Prototypes, these vectors that represent say different clusters or classes in say dataset. During training, these prototypes are iteratively adjusted, which is based on say input data and their corresponding class levels. Now during training phase, the prototypes are updated, which is based on say set of label training data. For each data point, nearest prototype is identical, and this prototype is adjusted, which depends on whether it belongs to same class as the data point. If classes matches, the prototype is move closer, and if it does not match, the prototype move further away. After training, the classification takes place by finding say prototype which is close to the input data point. Then the data point is then assigned the same class as that prototype. Learning rate, the parameter that control the speed at which prototype are adjusted during training. So you can say that the learning rate controls the step size. Higher learning rate means faster convergence, but it leads to instability. But with lower learning rate, it provides smooth adjustment. What are say different variants of LVQ such as LVQ1, LVQ2 and LVQ3? These variants have different update rules and techniques to adjust over fitting and moving and improve stability. Then we are having this Cognitron. It is developed by Kunihiko Fukushima in 1970. It is designed for, say, pattern recognition, and it is predecessors to convolutional neural network, which is called as CNN. The cognitron is introduced in such a way that it recognizes patterns in a hierarchical structures, and it leads to foundation concept in the development of more complex neural networks. Is composed of S cells and C cells. These S cells detect features, and these C cells learn to recognize pattern formed by these features. We are using this cognitron for image processing. Training algorithm. It involves unsupervised learning, which is called as competitive learning. In this learning, each S cell competes to become active on its input and bait, connecting it to neighboring S cells. So, what are say basic outline of training this network as following? So, first of all, we have to initialize the connecting bait between, say, S and C cell randomly. Then we have to present input patterns to the networks. Here each S cell computes its activation based on input patterns and bait. S cell with highest activation inhibit its neighbor and become active. Adjust bait based on active S cell and its neighbors. So here repeat process step from second to fifth until the convergence is achieved. Nuco, Nuco, Nuconitron. It is hierarchical multi-layered artificial neural network which is designed by Kunihiko Fukushima in late 1970s and early 1980s. It is inspired by structures and function of human visual cortex. This human visual cortex is a part of brain which is useful for visual processing. We can use this for, say, pattern recognition such as image recognition and handwritten character recognition tasks. So what are, say, different key features of Nucognitron? It includes first, say, hierarchical structures which consist of multiple layers, and each layer extract high level features from the input. Then convolution layer. These layers apply local receptive field to capture features like textures and edge. Then we are having subsampling layers, which reduces the resolution of the features map, and it contributes to invariance to small translation, distortion and scaling. Invariance to distortion. So the design allows the nucognitron to maintain robustness against small variations in the input, a critical aspect of visual recognition. So training algorithms, it learns the receptive field and bait to recognize patterns, and it is robust to small transformation in the input data. The training involves, say, unsupervised learning, and its primary emphasis on, say, feature extraction and hierarchical pattern recognition. The overview of Nigonitron training process. First one, say, unsupervised learnings. It does not require labeled data for training. It utilizes process of self-organization to adjust its based. In this network initially uh, used random weight during training. The receptive fields are adjusted to respond to certain features in the input data. Training with receptive field, it has layer with different types of receptive field. These fields help the network to extract and identify features from the input data. As input data is fed through the layers, the receptive fields are adjusted to capture a specific pattern such as edge or texture. Hierarchical learnings. So here hierarchical structures, it allows Nigonitron to build complex representation by progressively abstracting the features at each layers. Here each layer extract specific features and forward them to next layers for further processing. Competition among neutrons. The neutrons utilize competition-based learning mechanism to adjust its weights. So each layers compete to represent specific features. Neurons that best represent the given features are reinforced while others are inhibited. And this competition drives the self-organization process. Subsampling for robustness. So, invariance to small translation and distortion. This nigonitron employs, say, subsampling layers, which reduces the spatial resolution of the features map. And this subsampling process contribute to the network's ability to recognize patterns even when they undergo slight transformation. Fuzzy associate memory. It is a type of NN models which utilize pattern recognition and recall. It works by associating input patterns with output patterns, allowing them to retrieve similar pattern based on fuzzy logic rather than strict matches. These networks are useful for tasks like pattern recognition in noisy environment or where exact matches are not possible. Then this is the architecture of, say, fuzzy system architectures. Here we are having, say, a fuzzy file. It converts a crisp quantity into fuzzy quantity. Then here we are having intelligence system. So in intelligence system we are having different types of rule based system. This is developed by the say programmers. So based on this rule based system, here we are getting, say, fuzzified output set. But we can but in output we requires a crisp output. Therefore, we use here say defuzzifier blocks, which convert this fuzzy output into say crisp output. Comparison of fuzzy and say neural system. These are both computational paradigms which is inspired by biological process, but these have say different approach and application. So first approach to data handling. This fuzzy logics deals with uncertainty using linguistic variables and fuzzy rules, which represent imprecision information. This neural networks it learns from data using training, and in that process the error get minimized between actual and predicted output, and based on this error the weight bias are adjusted. Representation of knowledge. On this on this this fuzzy system use linguistic variables. Linguistic variable means such as say very high, very low, small, too small. This is called as fuzzy linguistic variables, and fuzzy set to represent knowledge in form of rules. But in neural networks, knowledge represented in form of say connecting bits between neurons. Data types. This fuzzy logic is well suited for handling qualitative and imprecise data. But this neural network, it is effectively for processing, say, quantitative data, especially in pattern recognition and classification tasks. Interpretability. This fuzzy logic system it provide human interpretable output due to their linguistic representation. This neural network lack interpretability, especially in say deep learning models where we are having say numerous layers between inputs and output layers. Training and learnings. This fuzzy system requires expert knowledge to define membership value and fuzzy rule base. It provides less emphasis on automatic learning from data. But neural network learn from data automatically by technique called as backpropagation, making it suitable for label training data where it is available. Application. This fuzzy logic is widely used in say control system, decision making and expert system where uncertainty and imprecision are prevalent. These neural networks find application in say diverse fields such as speech recognition, image processing, natural language processing, and predictive modeling. Fuzzy morphisms. It describes fuzzy structure preserving transformation between fuzzy set, fuzzy relation, fuzzy algebraic structure, or similar fuzzy construct. This morphism is used in logics and mathematics, and it is a concept for mapping that respects certain structural properties. In fuzzy logics, they are employed to understand how fuzzy concept and operation can be related or mapped to each other. Fuzzy set morphism. This map fuzzy set from one domain to another domain while preserving the membership structures. In simple terms, morphism for say fuzzy set A to fuzzy set B, it represents a function such that for every element x in A, membership degree of fx in B is consistent with the membership degree of x in A. Fuzzy relation morphism. This morphism between fuzzy relation is a mapping which preserves the fuzzy relationship structure between elements. Fuzzy algebraic structure morphism, which maps between algebraic structure in fuzzy context. A morphism in this context must preserve the algebraic operation and their fuzzy counterpart. Morphism in fuzzy logics, it is used in say various applications such as fuzzy control system, fuzzy data analysis, and fuzzy logic programming.